if you're hearing me clearly. Is everyone hearing me clearly?
Yeah.
Okay. I want to welcome everyone to my lecture today. And of course, today I'm going to be walking you through another exciting topic in statistics. Somebody said they can't hear me. Give me 1 second. I'm gonna if you're not hearing me, okay, if you are hearing me, I need all of you, those who are hearing me, to actually say yes, or you comment yes, because I receive a message from someone that he can't hear me. Okay, I think a lot of people are hearing me now. Maybe the person that is not hearing me, you need to adjust your audio. You need to look at your mic. Okay, so I think a lot of people are hearing me now. Okay, so before I get started today, I'm gonna say tomorrow I'm gonna walk you through practice questions, and I'm gonna give you information about, how the exam is going to be, the midterm one. Okay, but I send a message through announcement section. You can check about. I think I said something about the exam, but tomorrow in the class, what I'm going to do, I'm going to walk you through, the practice questions, the expectation, and some other stuff. So that is actually reserved for tomorrow. And today, watch out, your assignment 1 will be graded, and the solution to assignment 1 will be released. So that will be done today. Just watch out. Okay, so once again, I want to welcome you to this lecture. Give me 1 second while I share my screen. Okay, the focus in today's lecture is basically random vector and matrix concept, part 2. You remember we started part 1 on Thursday, and of course today we're going to continue from that. So I call this part 2. Okay, so in today's lecture, I'm basically going to continue to focus on the expectation and variance of the sum of random variables. You know, the other time we started summing random variables and we obtained the expectation. Okay, we also want to look at the variance of that as well. You know, we actually can't talk about expectation without also talking about variance. Then the next in the outline today, we're going to look at the concept of independence versus uncorrelated. And lastly, the focus is basically going to be exchangeability. Okay, we're going to talk about exchangeability. Okay, so let's get started. Now, I told you the other time, we actually work with some of random variable, but today we want to focus on the variance. But let me first revise with you. If you take a look at this guy now, okay, it's the same thing as writing x1 plus x2 until you get to xn. Okay, so which is the sum of random variable. Now, I want to tell you, we can also write it in a matrix form. Okay, so that is writing it in a matrix form. Now, you know, it's a U is the vector whose components are all equal to 1. So what I mean is basically, you know, when I have x equal to this, okay, and U equal to 1, 1, 1, 1, 1, okay, the transpose of that is basically this. Okay, now if I use this to multiply by that now, okay, it's just going to be, you are using 1 to multiply x1, 1 to multiply x2, until you get to 1 to multiply xn. So which is more or less x1 plus x2 until you get to xn. So which is the same thing as summation si. Okay, so that is writing that in matrix form. Okay, in matrix form, you're going to have a U transpose X. Okay, but in a scalar form, you're basically going to have the sum of X. That's what we're trying to say there. Okay, now talking about the variance now, we have a sum of the random variable. We've talked about the expectation. Let me quickly remind you, okay, if y equal x1 plus x2 until you get to xn, okay, expected value of y is basically expected value of x1 plus x2, okay, until you get to xn. You know, I walked you through the other time, and I said losing the law of expectation of linearity, okay, I'm basically gonna have expected value of x1 plus expected value of x2 until you get to expected value of xn. I think a chat came in. Somebody said, are we using u equal to 1 or u equal to, is u equal to 1? The u is a constant of ones, okay? U is a constant of 1. If you're talking about the other one that I walk you through, u is a constant of 1, okay? So the x1 plus x2 up to xn, okay, is actually but on this one now, I'm just trying to tell you, I'm when I'm working now, it's not this variance stuff. I'm just trying to remind you, you know, I'm reminding you of the sum of random variable that we talked about before. Okay, so here, this is more like the summation expected value of si, where I start from 1 to n. Now, this is the expectation, but now the interest is no longer on expectation, but the interest is on the variance of the sum of random variable. Okay, now if I have this as the sum of the random variable, now I want to find the variance of that. Okay, in matrix form, okay, it can be written in this way. Okay, in matrix form. Okay, that can be written in that way. Okay, but you're going to see, let us break it down. Okay, we want to break it down. You know, when you have the variance of the sum of a random variable, we're basically going to have, okay, a sum of you know, of covariance si and sj. Okay, this is the same as this guy here. You know, I walk you through covariance the other time, okay, where you are actually considering a pair of two different variables, and situation where I equal to j, then you have the variance. You understand what I mean? Now, if you take a look at this guy now, okay, we're basically going to have some variances and some kind of covariances in such a way that the general formula, okay, is basically going to be this guy here. It's basically going to be this guy here. Take a look at that. Now, I'm going to walk you through an example now. Okay, I'm going to walk you through an example now. Give me 1 second. I think I'm going to write here. Let's say, for instance, I have y equal x1 plus x2. Okay, and I want to find, and I know that expected value of y is expected value of x1 plus expected value of x2. I know that already from last week. But what am I seeking now? I'm seeking the variance of y. And the variance of y is the variance of x1 plus x2. You know what I'm doing now? I'm considering two variables, two different variables, s1 and s2. Now, this guy is going to be variance of x1 plus variance of x2. Okay, now when you have the variance of x1 plus variance of x2, then you're going to have plus 2 covariance x1 x2. Look at that. That is what you're going to have. Okay, so which means, take a look at this. What is the pattern here? It's more or less like I have, if I have X1, X2, if I generalize, that we actually go to variance of X1 plus the variance of X2 until I get to the variance of Xn. That is if I generalize to Xn. And here, I'm actually going to have different combination of Xi and Sj. Okay, so many combination of Xi and Sj. That's exactly what I have. That's exactly what I have here. Look at that. This is like having some of the variances. Okay, this is like having variance of X1 plus variance of X2. Okay, until you get to the variance of Xn. Okay, and this guy here now is having different pairs of Xy and Sj. Subject came in. Let me look at the chart. Somebody, can you show an example with y equal to S1 and X3? Okay, that's a good question. Okay, in that situation, okay, the variance of X1 plus X2 plus X3, okay, if you want to do, if you take a look at what I have now, okay, you can basically assume that you can, okay, let me do this. Let me stop my share. I'm going to stop my share now. I'm going to use my whiteboard. Give me 1 second. I'm going to use my whiteboard. If you're seeing my whiteboard, I need you to confirm if you're seeing my whiteboard. Does everyone see my whiteboard? I need everyone to confirm. Okay, thank you so much. Now somebody is asking me about the variance of X1 plus X2 plus X3. In this case, you know what you can do? You can let Z be X1 plus X2. Because of that, I'm actually going to have the variance of Z plus X3. Look at that. Now, when I have that, okay, it's going to be variance of Z plus variance of X3 plus 2 covariance Z S3. You see that? Now, you can split this guy again. You know, the variance, don't forget the variance of Z, which is the variance of X1 plus X2 equal what? The variance of X1 plus the variance of X2 plus 2 covariance X1, X3. Now, if you plug the whole of this, okay, into where you have the variance of that here, okay, now what are you going to have? So automatically, your variance of X1 plus S2 plus S3 is going to be variance of X1 plus variance of X2. Okay, now don't forget this guy, plus variance of X3. Okay, so when you have that guy, don't forget this guy, plus 2 covariance X1, X3. Now, when you look at this guy here, okay, you're going to have 2 covariance X1, X2, okay, plus 2 covariance S2, S3. Now, the person that asks me to do X1, the variance of X1, S2, S3, do you now understand now? Do you now understand now how you can expand that? You're basically going to see that when you have X1 to S3, you're going to have variance of S1, S2, S3, and you're going to have 2 covariance of, different pairs of X1 and S2, S1 and S3, and S2 and S3 that you're going to multiply by 2. Take a look at that. This can also be generalized. Okay, so take a look at that. That is how you actually are going to do that. Okay, so that is that. Somebody said, do we have 2 covariance of every possible pair? Yeah, you have it. You have the 2 covariance of, because you're talking about two different variables. 2 different variables is talking about 2 possible pair of that. Okay, so that is exactly what we have. Okay, now I'm going to stop this here now, and I'm going to go into the material. Give me 1 second.
Could you explain how to calculate the covariance?
Can you say that again?
Could you say how to calculate the covariance?
Oh, how to calculate the covariance. Actually, I'm gonna show you when we get to, example on how to do that. Okay. So if you look at the general formula here, somebody asked about that we're gonna have two. Of course, you're gonna have two. Now we have, you see two here. Anytime you have the covariance of different kind of pairs, there's always going to be two multiplied by that. So that's a general formula, and we're going to have the sum of the variances. Okay, now that is a formula for that. I think I'm going to show more example. Give me 1 second. Let me show more example. Take a look at this. If I have, the expansion matrix, okay, the expansion matrix that we also call variance covariance matrix. Let's say for 2 by 2, okay. If I have the variance of a vector matrix X for 2 by 2, okay, this is going to be variance of X1 in the diagonal. You're going to have variance of X1, X2, but in the off diagonal, you're going to have this. Here, you're going to have this. And you know what? Because it is symmetric, and symmetric will mean that this guy and this guy, they're going to be equal. Okay, if they are actually going to be equal, what are you having now? You are having two of that. You are having two of that. That is why the right diagonal here is the variances. The off diagonal will be covariances. And because they is symmetric, okay, if you take the transpose of this, you're still going to have this. Because of that, okay, which means for it to be symmetric, this guy has to be equal to this guy, right? And if it is up to that, then if I want to do that, I'm going to say two of that. That was how you normally see two covariance X1, X2. Even if you extend this to, X1, S2, S3, you're still going to see the same. Okay. I just wanted to take note of that. Now, somebody that talked about how we compute variance, covariance, I'm still going to walk you through that. Right. Four of us want to go through the theory here. Now, the next thing we want to talk about is uncorrelated. What do we mean by saying variables are uncorrelated? The variables are uncorrelated is a covariance equal to 0. I'm going to give you an example now. If the relation, if X represents percentage of time, the percentage of time the walk-in facility is used in a bank, and Y, if Y represents percentage of time, okay, drive-in facility is used, okay, if there is no relationship between them, if there is no relationship between the percentage of time the walk-in facility is used in a bank and the percentage of time the drive-in facility is used in a bank, in that situation, the covariance between them will be 0. And let me tell you this, what is implication when the covariance equal to 0? I told you the other time, covariance, we need covariance when we want to compute correlation. Don't forget, correlation will tell us, we measures what is the strength, or the strength and the direction of the relationship between two variables. If they are not related, the covariance of X equal S and Y will be 0. And when the covariance of X and Y equal to 0, you remember the other time I said the covariance of XY equal to expected value of XY minus the expected value of X, expected value of Y. If all of that equal to 0, what I indicate is that this is going to be equal to that. Okay. So expected value of XY, which it means a expectation of the product of X and Y will be equal to the product of the respective expectation. If that happens, it means X and Y are not related. Okay, they are not related. They are not related in the sense that you one, you cannot say anything about the other one. The fact that I know the percentage of time, okay, the working facility is using a bank, okay, we actually, that can not tell us the percentage of time, the driving facilities. Somebody said, how are we going to calculate the expectation of XY? Okay, let me now come back to a question asked by somebody the other time. How do we calculate the covariance of XY? Of course, I'm going to walk you through that now. And I'm also going to walk you through the question that comes in. How do we calculate the expected value of XY? I'm going to stop my share now. And I'm basically going to go into my whiteboard. Now, if X and Y are discrete, okay, if X is discrete, okay, and Y is also discrete, random variable, okay, let me even first tell you this. Expectation of S is this. Summation S, the probability of S equal to S. If for Y, it is summation Y, the P of Y equal to Y. But if I want to talk about the product, okay, I'm actually going to use summation XY. There's going to be two summation, and I'm going to have the probability. I'm going to have a joint, okay. Now, do you see that now? That is the formula. That is if I want to talk about joint, the product, okay? It has to be X sum. I'm going to sum for over X. I'm also going to sum over Y, and I'm actually going to be using the joint, okay? Now, the moment I get the expectation of X and Y, of course, I can get the covariance, okay? The covariance is just going to be the expectation minus that. Does that make sense to the person now? Okay, we need to find this.
How to calculate the joint?
No, the joint will be given. You're going to be given this one. You remember the other time I walked you through joint. A joint is going to be a function of X and Y. For discrete, they're going to give you in terms of a table where you're going to see the range of X and Y, the range of X, the range of Y, then you're going to see some probability associated with that. I demonstrated that last week. You can check my video on cardinality, where I gave an example of a four-sided die where we have 16 numbers and the probability is 1 over 16. Do you remember that? Okay, so we actually, but we're still going to do more example on that. I'm just trying to show you this now. Okay, now I'm going to go into the share now, into the material now. Okay, I think I've just walked you through, X and Y, when they are actually unrelated, if X and Y are independent, and of course, the expectation of the product is basically going to be the product of the respective observation. Now, take a look at this. In a situation, if I'm talking about the variance of X1, okay, X2 plus that. Okay, if X1 and S, I told you we're supposed to have this guy plus this guy plus 2 covariance, right? But if X1 and S2 are independent, this is going to be 0. You're only going to have the sum of the variances alone. There's not going to be covariances. I want you to take note of that. That is if X1 and X2 are unrelated. If I want to generalize that, where I have X1 up to Xn, okay, the variance of the sum will actually be equal to the sum of the variances. There's not going to be covariance. There's not going to be any covariance at all, because the covariances that we have is already 0 because X1 up to Xn are unrelated. I want you to take note of that. So what is this guy talking about? He's trying to say the variance of X1 plus X2 until you get to Xn is the same as the variance of X1 plus the variance of X2 until you get to the variance of Xn. okay, there's not going to be covariance at all. There's no covariation. There's only going to be variation within. And don't forget, the variation within is a variance. Okay, in a situation where x1, x2 up to xn are unrelated, then the covariance will be equal to 0. You are not going to have covariance at all. Okay, I just wanted to take note of that. Okay, now which is the law now? When you now take a look at the law, it's more or less like I want to find, when I started, we did this last week, expectation of the sum of random variable, okay, until you get up to xn is basically the summation, okay, of the expectation. You remember that, right? Okay, that's exactly what we are writing here in a short form. And today, we also said the variance of that, the variance of x1, x2, until you get to xn, okay, will be equal to the variance of addition of the variance of each variable situation where x1 up to xn are unrelated. Okay, if they are unrelated, okay, that's what we're going to have. And this is the short form of that. Okay, I just wanted to take note of that. Okay, this is a situation where they are unrelated. Okay, take note of that. Okay, now because of that, we're actually going to have an axiomatic characterization of independence. Okay, if x1 up to xn is independent, then we're trying to say the expectation, okay, of the product. Look at that. Expectation of the product will be equal to the product of the expectation. If you take a look at what happened here, it's like, taking this guy, okay, moving it to the back of that. That's exactly, you see that? That is exactly what you see there. And that's actually happened to the sum too. Look at the sum, okay? If you take a look at this, you have a variance of this summation. And here, what happened? Summation is going to come out, and the variance, we have tried the xi. That's what you have there now. Take a look at that. Okay, the same thing also applicable here, where that is moving out and the expectation is actually coming in. I just wanted to look at the pattern. Okay, I just wanted to look at the pattern. Okay, so that's exactly, because we may want to have a situation of a multiplication where we want to find the expectation of a product, x1, x2, or give me 1 second, expected value of x1, x2 up to you get to xn. That's what we mean. Expectation of a product. You remember that I said the expectation of a product, if I have the expected value of x1, x2 will be equal to expected value of x1 multiplied by expected value of x2 if and only if S1 and S2 are independent. Okay, now that is why you're going to have the expectation of the product to be equal to that. Okay, those of you are asking, how am I going to obtain the expectation of the products? Okay, if X1 and X2 are independent, the expectation of the product is just going to be the product of the respective expectation. If I now want to generalize, this is generalization now. If I want to have expected value of X1, X2 until I get to Xn, okay, if X1 up to Xn are independent, I'm basically going to have expectation of X1 multiplied by expectation of X2 until I get to expectation of Xn. And if I want to write this guy in short form, I'm basically going to write that, okay, which is basically going to be a product. Now, you remember, somebody just asked me now, why do we have, somebody said, does h of s equal to the probability? Okay, that's a very good question. You remember the other time when we are trying to say probability is a special form of expectation. If a random variable is an indicator, we are able to find that the probability of I equal to P. You remember in Bernoulli, right? Do you remember in Bernoulli? And what do we mean by that P? It means S equal to that, the probability of that equal to that. Okay, and that is I believe that is what you're trying to talk about in your question. Okay, now Another thing that I want to talk about now. Now take a look at this. We have f of x, and this is a product of all the x's. Okay, maybe what I'm trying to say here, this guy means f of x1 multiplied by f of x2 until you get to f of xn. Don't forget that this guy here is more or less like a vector. It's like a joint, f of x1, x2 until you get to xn. You remember the other time we're able to prove that if x1 up to xn are independent, the probability joint, okay, the probability of the joint would be equal to the product of the marginals. You remember we've been able to establish that before, right? Okay, now that is what we're trying to say here. Okay, this is like writing it in a, in a scalar form, and this is writing in a short form. Okay, that's what we're revisiting. And you remember the other time when x1 as a support of x1, if x1 lies in x1 and x2 lies in x2 and up to xn lies in xn, okay, the only condition under which x1 up to xn are going to be independent is when the support of the vector is actually in the product of, is in the Cartesian product. You remember that? Okay, you remember that? In the cardinality of the Cartesian product will be equal to the product of the cardinality of each sample space for each of the variable. You know that, right? That is exactly what we're talking about here. That if the support is a product in the Cartesian product, okay, where SI is the support of XI, of course, this is basically going to hold. That is exactly what we mean. This is going to hold. I think I walked you through something like that before. Okay. And when you now take a look at this, you remember when I was saying multiplication comes out of expectation. When you consider a case where HI equal to I, I just mentioned indicator function the other time, right? I mentioned indicator function, right? Okay. If I now want to find the joint probability, okay, the joint probability, because of the fact that the probability of xi equal to this is equal to the expected value of that. You remember that? Okay, the probability of x2 equal to this will be equal to the expectation of ix2. You remember that I showed you before that expectation is a special case of probability. I mean, probability is a special case of expectation. You remember that? So if I now want to talk about joint, all what I'm just going to do, multiplying all the expectation is like the same thing as multiply all the probability. Because we've been able to prove the probability of xi equal to si will be what? Expectation of I of xi, indicator of xi. That is exactly what I'm trying to do here. Okay. And at the end of the day, that will give us the product of the functions, of the respective functions. Don't forget, this guy here is going to be f of x1. This guy here is going to be f of x2, and so on like that. Okay. Just wanted to take note of that. Okay. Now, I think I've walked you through independent versus uncorrelated. Let me tell you, if X and Y are independent, they are said to be uncorrelated. I'm going to say that again. If X and Y are independent, then they are said to be uncorrelated. They are independent because there's no relationship between them. I'm going to say that again. They are independent means no relationship between them. And if X and Y are independent, the covariance of XY will be equal to 0. And don't forget the covariance of XY equal to that. If that is equal to 0, what we're trying to tell the world, the expectation of X and Y would basically be equal to the product of the respective expectation. That is exactly what we mean. Okay, I want to walk you through an example now. Independent versus uncorrelated. We are still on that. Okay, here, what are we trying to say? Let S be a non-constant random variable such that X and minus S have the same distribution. Okay, Now, an example is a uniform distribution. If you have a range from -2 to 2, you have a number line. This is the center. Okay, this is 1, 2, -1, -2. We'll take a look at that. And this is uniform. Now, then x and y equal to s squared, okay, are uncorrelated. What do we mean? We want to see if this is for x, okay, automatically y, okay, if I squared -2, 1, I think I'm actually, if I square, I'm actually going to have 0, 1, and 4. Because when you square any of that, okay, when you square 0, it's going to be 0. When you square -1 and you square 1, don't forget the function is s squared, it's going to be 1. When you square -2 and you square 2, it's basically going to be 4. Now, how do we show that x and y are uncorrelated? Do you remember what we did the other time? You can look at it from the Cartesian aspect. The support of y here, this is the support of y. This guy is the support of x. Okay, if you can find the Cartesian product of x, which is the x cross xy, okay, the cardinality of x here is basically 1, 2, 3, 4, 5. The cardinality of y is 3. Don't forget you have 3 elements there, right? What the cardinality of the Cartesian products now is basically going to be 15. If you cross these 3, s that by that, you're going to have 15, where you'll be able to have the probability of s take a value and y take a value. Okay, that shows they are going to be independent. Okay, they're going to be independent means they would basically be unrelated. Okay, and that is exactly what we're trying to do here. We want to prove that the covariance of xy, okay, if they are uncorrelated, okay, if I substitute s squared for y, I'm actually going to have this. If I now want to find the covariance of that now, okay, of course, you know that the covariance of xy is expected value of xy minus expected value of x, expected value of y. You know that, right? Okay, if my x now equal to s squared here, what's going to happen? It means in the product, you're going to have x times s squared, which is this guy here, and you're going to have expected value of s and expected value of s squared. That's exactly what you have there. Look at that. That's what you have. Okay, so I just wanted to take a look at that. Okay, but I think I'm going to have a kind of let me come here and show you something. If you take a look at what I have here, okay, if you plug in your negative, because don't forget some part of x here can be negative, and don't forget that -2 and 2 have the same values in y, which will give us 4, because you are squaring, right? -1 and 1 we do the same. If you come here now, instead of x to the power 3, because you can have the fact that -1 and -2 can give you 4, -1 can give you 1 in 1. The same, what -1 is going to give you is what 1 is going to give you. What -2 is going to give you is what 2 is going to give you. If you plug that in here, you're basically going to see that at the end of the day, this is just going to be a minus covariance xy, because you know why? This guy here is the covariance of xy. If you plug in that of negative, if you bring out the negative out, automatically you're going to have this guy here. And which is God. And this guy is covariance of xy, which will be a negative of that. Look at that. That is how we got that. So that was why we said the third equal sign being that x and minus x have the same distribution. Okay, so take a look at that. But since the only number s that satisfies s is equal to minus s is 0, then we have the covariance x y equal to 0. Let me see, somebody said, Are we proving that X and Y are independent by proving that covariance? No, no, we are not proving that, you know, when the covariance of XY equal to minus covariance of XY, this is no longer independent anymore, because we expect to have that this guy, okay, will actually be equal to the expectation, okay, of XY minus expected value of X and expected value of Y. They will all be equal to 0. That's exactly what I'm trying to say. Independent is not saying that. The independent is only saying that the covariance of XY equal to 0. Okay, the person that shall with me. Okay, now if you want to justify what I've just said, okay, you can, you know, I told you you're going to have the support, that is support for X, okay, and this is the support for Y. You know, is 0, 1, 4. When you square 1, it's going to be 1. When you square minus 1, it's going to be 1. Now, if you cross this, okay, do we have, you know, by Cartesian product, we actually need to have 15 entries. By Cartesian product, we're expected to have 15 entries. But let me tell you this. Don't forget we're using this function, right? Now, why do we have this to be 0? Now, minus 2, 0. Is it possible if this is X and this to be Y? This is not possible, because don't forget, your Y is S squared. If I square minus 2, it's not going to give me 0. Okay? And so it means this combination is not possible. That was why you put 0 here as a probability. Now, can we also, this guy here means minus 2 and 1. Minus 2, 1. When S equal to minus 2, can Y be that? Don't forget your Y is S squared. Okay? That was why you have 0 here. But look at this combination here. Okay? You don't forget you are considering so many pairs. They're going to be 15 pairs. Minus 2 and 4. Yes, this is possible, because this is X, this is Y. Don't forget your Y is S squared. Do you all get that? And you're basically going to see that will occur 1 out of 5. How do I know it's going to occur 1 out of 5? Because I have 5 entries in S. Okay, I have 5 entries in S. Who is there anyone who doesn't understand how I set up this table? Is there anyone who doesn't understand how I set up that table? Now, let me tell you this. You're going to see here that because of the fact that when you set up the Cartesian product now, the support is not a Cartesian product in this case. If you consider the other what we did the other time, when we cross, you get the same 1 over 16 when you have 16. When the cardinality of the Cartesian product is 16. You remember the example that I walked you through, but it's not the same here. The support, you know, I told you, it is only when the support is Cartesian, okay, product. I'm going to say that again. It is only when the support of X times Y, okay, is Cartesian product, then that is where we can say they are independent. In this case, X and S squared are not independent. And this is the proof. You know, you will discover that when we try to do that here, this does not give us 0. Okay, for them to be independent, the covariance of X and S squared, the covariance of X and S squared supposed to be 0 if X and S squared are independent. Of course, if you want to look at the common sense, they should depend. They should depend in the sense that S squared depend on X. Before I can get S squared, I need to square X, isn't it? And that is the reason why you got this guy here, why you got the covariance of XY to be negative covariance of XY, because if they are independent, the result should be 0. Do you now understand the meaning of this now? Do you now understand the meaning of that now? Okay, so they are related. That is what I mean now. They are related. If they are related, okay, then it means they are not independent. I'm going to say that again. If they are related, okay, if they are related, then they are not independent, okay? And that is what we're trying, if you take a look at what I have here. And that was why I look at that. Okay, the support is not a Cartesian product, so the variables are not independent. And from the common sense, you don't expect this to be independent of that, because if you are s squared depending on x. When you square x, you get x. And when you look at the element in the Cartesian product, -2 and 0 in combination does not exist in probability. That was why you see 0 and 0 in that regard. Okay, just take note of that. Okay, so I think I'll just walk you through that. The last for today is what we call exchangeability. I'm going to spend additional 3 minutes. I have 4 more minutes to go. What do we mean by exchangeability? Exchangeability actually means if I have a function, a mapping from S to T, okay, if that is invertible, what do we mean by being invertible? Okay, if I can find the inverse, okay, I have inverse G where I want to go back now, go back to T. Here I was going from X to T, but I want to go back to where I come from. Okay, in that situation, then the G of f of s is going to be equal to that, and the G of f of y would be equal to that. And what does that mean in the actual sense? I'm going to tell you now. If I have x1, x2, up to xn, and the probability distribution of that can be, if you reorder this, maybe you reorder it as x2, x1, x3, blah blah like that. If the probability distribution is the same, okay, if the probability distribution of that is the same, after ordering that or after rearranging that, okay, then we're trying to say the variables are exchangeable. Okay, that is what we mean, that the variables are exchangeable. I'm going to say that again. The variables are exchangeable. Okay, if you're trying to reorder that, and this is exactly like if I have f of x1, x2, and s3, if it's the same thing as this. Look at that. If it is the same thing as that, then it says the x1, s2 up to s3 are exchangeable. That is exactly what I mean. Now, some of you may be wondering, why do we need exchangeability? Okay, I'm going to tell you practically, but I'm going to say this. This is the generalization. If x1 is up to xn, and this is the permutation of that. Permutation is like I rearrange that. Okay, if the arrangement that was done, if I still find the distribution and say they still have the same distribution, then I'm going to say they are exchangeable. Now I'm going to tell you the application of this in statistical analysis. In statistical analysis, give me 1 second. I'm going to stop my share now. Okay, what do we mean by exchangeability in statistical analysis? When in statistical analysis, we normally say groups are exchangeable. Okay, groups. Okay, let me just say, let me just write this. Give me 1 second. Exchangeability. 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 Absorption implies that groups are exchangeable. Now, when you are performing experiments, you have a treatment group, you have a control group. This is a control group, and this is a treatment group. Okay, in statistical analysis, for instance, let me use COVID vaccine as an example. When the Pfizer, Moderna, and the AstraZeneca, when they are trying to test the efficacy of their vaccine, they actually injected participants with the virus, right? And they will randomly assign participant into treatment group and into control group. Okay, now those that they're actually going to use the principle of randomization in such a way that the assignment of participants to groups will be random. Anyone can go into any of the group. Now, exchangeability means if I switch some people in this group with some people in this group, I'm expecting the outcome to be the same. Outcome will be the same. I'm going to say that again. Exchangeability in statistical analysis means when you exchange, okay, participant in control group with the treatment group, the outcome should remain the same. And that was what I was talking about the other time, that when I have X1 up to Xn, okay, and I rearrange them and I find the probability distribution, it should give the same when they are exchangeable. And let me tell you this. The example I cited here, they're basically going to be exchangeable if the relationship between treatment and outcome is not confounded. I'm going to say that again. If the relationship between treatment, okay, and control is not confounded, okay, we expect to have the same income even though we switch the element, the participant in each group. But I want to tell you a situation where exchangeability will be violated, assumption will be violated. If you have patient with more severe version of a disease in one group, for instance, I'm talking about, if you look at the COVID now, some could have a severe symptoms, some could have a mild symptoms. Now, if you want to look at the efficacy of vaccine and you now put more of people with this, more of a patient with a severe version of a disease in one group, okay, compared to the other group, when you exchange, in that situation, the outcome will not be the same. I want you to comment if you really get that. I'm going to say that again. When you put more of patients, okay, that have a severe version of a disease in one group than the other group, don't forget, okay, when you exchange the control for treatment, your outcome will not be the same. In that situation, exchangeability assumption is violated. In statistical analysis, okay, exchangeability assumption must hold, particularly in this kind of experiment where you basically want to determine the efficacy of a drug. Did you get that? If you understand my explanation now, I need you to say yes, or you comment yes. Okay, that is it. And you know what? That is where I'm going to stop today. Is there anyone who need clarification before I go today? Is there anyone? Is there anyone? Somebody asked in the chat, do we say that the variable themselves are changeable? In other words, if x1, x2, x3 equal to f of s2, s3, s1, are the x's themselves changeable or the function? Now, let me tell you something. The only condition under which they are exchangeable is when their function are equal. I'm going to say that again. What do we mean by the function? That is the probability distribution of them. If I have x1, x2, s3, okay, and I permutate that. What do we mean by permutation? You know, we could arrange, we could, trying to alter the arrangement. When you alter the arrangement, when the probability distribution before you rearrange and after you rearrange is the same, then we're going to say the variables are exchangeable. For variables to be exchangeable, their function have to be the same. And that was the example I cited. When we are talking about, you have two groups in statistical analysis where you have a control group and you have a treatment group. Okay, the only situation, if you want to switch, okay, don't forget in the treatment group, okay, I use the example of a vaccine the other time, when the companies were trying to validate their vaccine, okay, when they were trying to conduct the efficacy of their vaccine, what they did, they actually partitioned participants into two groups. Some received the vaccine, some did not receive the vaccine. Don't forget they injected virus into all of them, and they partitioned them into two groups. Those in the control group did not receive the vaccine. Those in the treatment group received. What I'm trying to say, for exchangeability now, if things were done, if the assignment of the patient were done, okay, using the principle of randomization. I'm going to say that again. What do I mean by principle of randomization? When you are assigning, because when you are conducting an experimental study, there's a difference between experimental study and observational study. Experimental study, you randomly assign the participant into different groups using the principle of randomization. Okay, they have equal chance of being assigned to any of the group. What I'm trying to say now, when the way you assign, if they are independent, if you use the principle of randomization, okay, it means when you now switch the treatment group for the control group, okay, which means if the outcome remain the same, then the patient are exchangeable. That's what I mean. What is the outcome this time around? It's the probability distribution, which is the response. But the only situation where they're going to be the same, that depends on the way you assign the patients to the groups. You shouldn't be biased in the assignment of patient to groups. So in statistical analysis, exchangeability is highly required. Okay, that's exactly what we mean. So I've walked you through this mathematically, and I've explained to you, practically. Okay, this is going to be the end of my lecture today. I hope you guys enjoying it until tomorrow. But you know what I'm going to have tomorrow is going to be, I'm going to review practice question for the midterm. I'm going to give you a lot of stories tomorrow. My expectation, in the exam, the areas is going to cover, among other information. I'm actually going to unfold that tomorrow. But before I go, is there anyone want to ask question or unique clarification? Is there anyone? Okay, in the absence of that, make sure you stay safe and have a lovely day. Bye for now, everyone.
Thank you.
You're welcome.